Hello, my name is Yao. This video is to present the paper of a transparent antenna using metal mesh for ultra-wideband MIMO applications. Transparent antennas can be integrated on various building materials with little visual impact, which can facilitate flexible deployment of massive wireless devices. This paper presents a transparent ultra-wideband MIMO antenna based on a welded metal mesh structure. In Figure 1, the CPW-fed UWB element with FR4 substrate is hollowed to weld metal mesh style. Thick and thin wires are used where the current distribution is strong and weak respectively. For example, thick wires are used on the edges of the patch, and the thin wires are used in the center. Although there are some changes in S11 shown in Figure 2, the hollowed element still retained the working mode of the solid element, and the bandwidth remained unchanged. Then, 4 transparent elements are formed to a MIMO antenna array. In Figure 3a, the ground planes of elements are connected by a criss-crossing network. The network not only increases isolation between elements, but also creates more design space for the decoupling structure on the back of the array, as shown in Figure 3b. The decoupling structure is conformal to the meshes, and the transparency is not affected. It can improve the overall isolation within the whole operating band. Figure 4 shows that with the aid of decoupling structure, the coupled current on other elements is very weak. The S parameters are shown in Figure 5a. UWB is fully covered by the resonant band. Both the simulated and measured S21 and S31 are lower than -20 dB. In Figure 5b, the radiation efficiency is greater than 83%, and the measured gain varies from 3 to 7.3 dBi. Figure 5c shows that the measured channel capacity is close to the upper limit of 4-element MIMO antenna. Figure 6 shows the prototype and that mount on a window. In summary, the proposed transparent antenna achieves high transparency, ultra-wideband, high efficiency, and low coupling. It's a very promising device to be applied in the indoor wireless infrastructure.
Hello everyone. This video is about a dual-polarized Endfire antenna with ultra-wideband and high isolation for 5G mmWave multibeam systems. Firstly, we will introduce a mode composite SIW, which is achieved by incorporating a stripline into the SIW. Thus, this structure has 2 fundamental transmission modes, ATEM mode provided by the stripline and ATE10 mode provided by the SIW. According to calculations, TEM and TE10 modes are orthogonal. Thus, the mode composite SIW can be used to design high-isolation dual-polarized antenna. The magnetoelectric dipole is characterized by wideband and stable radiation. When the SIW operates in the TE10 mode, surface currents exhibit a 180 degrees phase shift between the upper and lower metal layers, which can function as a broadband balun. Thus, we innovatively developed a SIW-fed magnetoelectric dipole as the vertically polarized Endfire antenna. Then, based on the SIW topology, a stripline-fed tapered slot antenna is designed as the horizontally polarized Endfire antenna. And, owing to the wideband property, these 2 antennas realize an ultra-wide bandwidth of 80%. A dual-polarized Endfire antenna with shared aperture can be developed by combining the magnetoelectric dipole and tapered slot antenna. To ensure that the magnetoelectric dipole can be excited, long slots are etched to separate the SIW ground. The middle portion of the magnetoelectric dipole is cut to avoid short-circuiting the TSA feed. Thanks to this innovative design, the proposed dual-polarized Endfire antenna realizes an operating bandwidth of 62% covering 23.25 to 43.75 GHz. The port isolation level is higher than 35 dB. Lüneburg lens can generate stable radiation beams in a wide-angle domain, which is a promising solution for low-cost multi-beam systems. To satisfy the requirements of 5G communication systems, we designed a multi-beam antenna system composed of 7 dual-polarized Endfire antennas and a 3D printed Lüneburg lens. The measured results indicate that the multi-beam antenna achieves an overlapped bandwidth of 58%, covering 23.45 to 42.8 GHz. The port isolations between the HP and VP antennas exceed 32 dB. The mutual couplings between polarized antennas are less than -18 dB across the working band. This as measured beams show that a beam scanning range of plus or minus 66 degrees has been realized by the 7 radiation beams, and the gain falloff is less than 1 dB. This table compares the presented dual-polarized Endfire antenna and several state-of-the-art antennas of the same type. The presented dual-polarized Endfire antenna demonstrates superior bandwidth and isolation, and is suitable for 5G millimeter wave systems.
Hi, everyone. It's my great pleasure to present our work on an ultra-wideband frequency-reconfigurable tightly coupled dipole array with wide beam scanning capability. Modern communication systems demand multifunctional terminals and ultra-fast connectivity. These demands drive antenna arrays to achieve ultra-wide bandwidth, high radiation efficiency, and wide beam scanning capabilities simultaneously. Tightly coupled dipole arrays, or TCDAs, are known for their UWB capability and compact size. However, when the bandwidth exceeds 10 to 1, the short-circuit bands can limit further extension. It happens when the distance between the dipole and the ground plane is about a half wavelength and its integer multiples within a specific frequency range. Additionally, achieving wide scanning performance and ensuring effective UWB feeding design remains challenging. To address these challenges, we developed an innovative frequency-reconfigurable tightly coupled dipole array, or FRTCDA. Here we show the unit cell structure and fabricated 14 by 14 array prototype. The developed array has 3 key innovations to achieve its superior characteristics. Next, let me briefly walk you through the design. The first key innovation is the reconfigurable layer, which functions as a phase-shifting layer. It converts unwanted out-of-phase ground plane reflections into in-phase reflections, avoiding short-circuit bands with low insertion loss. The pin diodes enable switching between 2 reconfigurable states, a low-band state from 0.37 to 0.93 GHz and a high-band state from 0.85 to 5.85 GHz. Most importantly, unlike traditional solutions of loading highly lossy materials, this bandwidth reconfigurability method achieves a high radiation efficiency of over 95%. The second innovation is the DLDS-CLLS structure. It mitigates impedance variations during beam scanning, supporting wide-angle performance. This is demonstrated by the converged impedance loci of the array element after including the DLDS-CLLS. It allows beam scans up to 70 degrees in the E and D planes and 50 degrees in the H plane with VSWR less than 3, while maintaining high radiation efficiency. The third innovation is the specialized feeding scheme, including Klopfenstein tapered balance, combined with capacitance-loaded shorting pins. These pins are custom designed to reject the unwanted common mode resonance in the high-band state and the loop resonance in the low-band state, ensuring UWB feeding in both reconfigurable states without bad resonances. The developed array achieves an active VSWR below 3 across 0.37 to 5.85 GHz through 2 contiguous bands. Measurements of the 14 by 14 array prototype confirm the simulations. Considering scanning, the array achieves enhanced scan angles up to plus or minus 70 degrees in the E, D planes and plus or minus 50 degrees in the H plane over both states. In summary, our array achieves outstanding performance with ultra-wideband coverage, enhanced scanning capability, and high efficiency. It offers a promising solution for advanced communication, sensing, and imaging applications. Thanks for your listening.